The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spent a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, the group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I'm geologist Philip Ong, here with Mr. Dane DuPont of HawaiiTracker.com, bringing you guys another Kīlauea and Maunaloa volcano update. Today, Thursday, August 26, 2021, we came to you guys a couple days ago with a bonus episode as the earthquake swarm on Kīlauea began and associated with an intrusion, so we're going to cover that event in depth here today, as it now appears to have either paused or ended at this point. We will be collecting questions. Dan will be collecting questions in the chats and answering what he can, but we'll also be discussing live viewer questions towards the end of our sharing today. And let us know if you have any issues with the sound or with the buffering or whatever it may be. Dane is there for that as well. All right, so we're going to start off today with the earthquakes on Kīlauea. And I'm going to start off with this image here. This is an image from the USGS that was shared on their social media. And this is just showing, we'll go through this in a little more detail shortly, but this is just showing the pattern of earthquakes colored by time over that not quite 2-day period, maybe 41 hour period or so, that all those earthquakes swarmed during, right all through there. So, but to start off, let's go back to the current earthquake map and just show you guys what's happening now. So here's the main USGS earthquake page, and I have it selected to showing earthquakes only in the map area, which is this setting over here. And by doing that, I can see that within this square, which is the area I'm interested in, I'm not interested in anywhere else on the island right now, although I realize there are other earthquakes elsewhere. As far as the swarm is concerned, right through here, that last earthquake, ordered by time to newest first here, that last earthquake was a 2.1, and it came in last night at 10:10 p.m. So it's been a while since there has been any event through here. Right, 2.1. There was a 1.9 that was also last night. There's 2 orange ones right through there, and otherwise you can see going back, the rest of the sequence is all in yellow there. So just to point out that they're not ongoing any longer, but there might be a few events that happen, here and there sporadically as the area continues to adjust, and that's okay. Just having an earthquake or two in the area doesn't mean it's going to start back up necessarily. It just shows that it's still settling and adjusting to that massive change that just happened over the last few days. So that's the bottom line there. All right, so let's show you guys here the seismic graphs on the summit. Give you a different view of this, so you can see all these ink splotches on here. That's all little earthquakes, a whole bunch of them. And when you see more of this thicker blue background through here, that's the area of higher tremor, something like that. Or if I scroll it over to this one through here, this kind of back and forth activity, and kind of jiggling of the pen, so to speak, up and down. So sometimes it's a little easier when you zoom it out to see where the tremor may be. There's a period of tremor there, and something going on now. In fact, maybe that might be more of the surface wind and all that, right? And this may be more of the background effect compared to the event that was happening more so yesterday, when the real tremor in this graph is actually up here. So that's more what it looks like. A lot of earthquakes in short sequence in the ground, shaking almost continuously during that time in between. So it didn't seem like it was very continuous for very long in that area, but it was happening, and you can see the pattern overall. It's not. We don't see nearly as many. There's still a few earthquakes, but not nearly as many. So it really is winding down there. All right, let's cut to the chase here. Let's just share with you guys a little bit of the history of what happened. The USGS on Tuesday, early morning, raised our volcano's alert level from from advisory /yellow to watch/orange, right? And I have 2 different terms because one of those is the aviation code, and one of those is the alert level. So alert level is the advisory, and the aviation color code was yellow. It went up to orange a couple of days ago, and then just today, without going into all the text of it, today they dropped it back down from orange back to yellow advisory. So it was a 2-day change, and we had the benefit of having daily updates for the last couple days, and now we're going to go back to likely our weekly updates from the USGS. So we'll see what happens. Of course, if things change, if this activity does lead to something else, then it ramps up, and they can put it back up. And maybe just a short note, just short talk on this day. And it seemed like it was a lot more deft and a lot quicker to react from the USGS, and the alert level went up pretty quick, came down pretty quick. So yeah, that's different from the last time, yeah?
Yeah, night and day difference on that one. Seems like they learned the lesson of the last one. And for those that don't remember how the last eruption began with in terms of the alert levels, we were at green, we had an intrusion. The USGS were going to bring it up to yellow, and before that was published or made public, it erupted that night, like the night before. So it went from green, skipped yellow, skipped orange, straight to red,
right,
and then down from there as the eruption progressed. Here we actually, it makes more sense to me, at least, how the alert levels are being utilized.
Yeah, absolutely, yeah. And the last eruption was one where we weren't sure if there was going to be any magma water interaction, and so I could see why we'd go up to red, certainly at that point, even with just based on that, right?
Right. It was just the period of time between the intrusion of magma and the eruption was a couple weeks.
Right.
Right. So there was time in there, and now we can see that the USGS can make these moves rather quickly if the situation warrants it, which is good. That's where we want them to be.
It's fantastic. I love to see the USGS flex that ability, right? That's what we'd like to see, is a quick response up and down either way, right? And so on a slight tangent, we'll await some change with Maunaloa at some point, and we'll can discuss that further, at the end of our update here when we talk about Maunaloa very briefly, because spoiler, nothing's really changed in Maunaloa. All right, so back to Kīlauea here. We're gonna look at this map, and let me zoom it out here so I can show you guys. This is actually a tweet from the USGS, and he talked about some activity diminishing, no eruption expected. This is a summary of that volcanic alert activity notice that you guys just saw. The title of, in fact, right? You can see 478 earthquakes in total, mostly between magnitude 1 and magnitude 2, at depths of 1 or 2 kilometers, 0.6, 1.2 miles below the south part of Kīlauea caldera. Ground information was rapid, but has leveled off, and so we'll look at all of that in detail here too. But the main image here, if you look at it, is actually giving us two cross sections, right? So what this actually is if you imagine looking at this face from this direction, like if you could look at a slice of the Earth that went down at depth 4 kilometers down, right? So actually the volcano surface is somewhere around 1. It might actually go, slightly higher, something like that. So everything else is underground there, and so we're getting a cross section from the side here. And so the first thing I notice, there's one on the bottom as well. We'll look at that one too. But the first thing I notice here is this is a view of the earthquakes that we haven't been able to get online with the automatic tools. So let me zoom it in here. You may be able to tell that there are actually two different areas, right? There's one area that's shallower, and it's kind of with the top along this dashed line, which is, if I scroll down here, 0. That's right around sea level. And then there's a second group, a larger group, wider, over here, that seems to go between 1 and 2 kilometers below sea level right there. And so there's a little bit of a gap in between right there. That's fascinating to see. You can see that really the earthquakes that occurred, here's how you can look at this. The earthquakes that occurred closer to that west vent right up here. This goes straight across. Those ones are over here. And they're kind of apart from everything else, so maybe there's some connection to that old vent and magmatic system still, but it's a seismic in between, the area in between, but maybe as it feeling some pressure change, it's adjusting as well, possibly. That's the thing. But really not a whole lot of change happening in that in between. Most of the change is happening here in the southern area, right? You really see the section down here, right? From here down. And so we can see these teal and yellow and green and blues. That's kind of off here to the side. There's the yellows and blues and greens right there. So really those are all the not part of this main cluster. What we're really interested in looking at is this big clump right over here, because that's what this and this maps out to on this map, is this cloud right over here. Right? So a couple of things to notice there. Yeah, that's just a view cut across from the side. This one, where most of the events are located, is actually fairly long north and south, right, and skinny east and west. So that suggests something like a dike. It might come in something like this, right? So that in the map view, and it can push into the sides. And you can, if we look at this cloud over here, this lower cloud, it actually has some depth to it, right? So it might be something like 1 kilometer tall, more or less. And not to say that exactly everywhere that you see earthquakes is where there's magma, but you'd imagine that earthquakes are pushing on the edges, and the rocks on the outside edges close to the magma are the ones that are actually cracking and expressing that. So this upper cloud, in contrast, if we look at it over here, right, see where these reds are, there's some greens and yellows, right? They're actually all spread out along this whole pad right over here. And kind of in that oval right in there. So that's a little bit different. That might be something that we call a sill, where it's a flat sheet. Right? So a dike is a vertical sheet coming in, and it might have fed something shallower that's flat up into the side. And so that might be what we're seeing here. We can look at it in a little more detail, but that's what's suggested. That's why it looks like these are a little bit more spread out And that's why these look like they're more on top of each other, more clustered together, as you're going to really have. You do have more events. I think this was the larger event overall, but also the geometry is different, right? They're not all just spread in the same, they're not all overlapping in the same surface projection, right? So that's how it looks on this north to south cross section. If we actually scroll down here, we can look at the east to west. We get a second one over here, which is really cool. So once again, here's our volcano surface. Somewhere around this -1, that's 1 above sea level. Our summit actually is at maybe 1.2 kilometers. At its very, very tippy top. The bottom of the pits, where the lava lake crust actually sits, is about 750 meters. So that's actually down over here, right? So maybe if I were to draw the profile of the volcano on here, it might go something like that. Yeah. Just very, very roughly. So, and everything is smushed, of course. So we're not really getting everything, any distinction north and south, right? So that's similar to the depth of that Halema'uma'u shallow reservoir, but you can see it's actually offset to the south of it, of that whole area, right? So right over here, actually. So there's that shallower area, and you can see it's actually pretty spread out in this view as well. Pretty obvious to tell that it's spread out both in east-west and in north-south. That's what makes it a flat-looking thing. And this one, you do see this cluster, right through here. It looks like maybe you have a bigger cluster right there. Maybe I can zoom this in more for you guys. That might be the max I can get. There's a cluster right there, and there's a little bit of a tail. It's a little bit flatter and lower down, right over there. And there's a couple blues and orange, couple yellows. And let's look back. Let's go up here and look and see where those blues and oranges and yellows are. So actually, here they are, blues and oranges and yellows. These are off to the side. So those are interesting. Those might be the larger scale structures adjusting to the intrusion of magma through here, and in the smaller earthquakes, there's a smaller adjustment of rock closer to the magma. Right? So other changes a little farther away. But that's not exactly part of our sequence. That's kind of off to the side. That's the interesting thing. And if it is something that magma is pushing in, then maybe it's also one of these flatter zones, right? So maybe you could have some combination of a dike and a sill and possibly another sill, something like that, yeah. Or you could be activating structures that are old fault lines that the magma is just able to push them, and you can actually not have exactly a sill, but the magma can be pushing a piece of rock that slides that particular fault that has an orientation that's more horizontal, similar to a sill, that might cause that pattern of earthquakes like that. So really, that's what this little till ends up being, which means we can focus on this cluster as being really the center of where the dike's putting in. And when we look at it, it's not that wide east and west as we described further up, right? That's our cluster right there. So you can see it's still tall, and we're basically looking into it. It would probably be something like this, and it's pushing rocks in the sides both directions, right? And then maybe it feeds up, and maybe right here you have that flatter sheet. So that's an interesting thing. I can't really draw it too well in 3D here. I'm doing what I can with my Madden pen. And map you once again. That's what we can take out of this really cool image, right? And the USGS monitoring page does have some automatic tools, but and so does Iris, but nothing with this resolution where we can look at this very, very, very shallowest part and break down this upper 5 kilometers, right? Really, with this resolution, usually everything is just scrunched up, and 0 to 5 is all just one small band, and then you look at 5 to 15, and so on and so forth. And so we're totally ignoring all the deep stuff here because this was really a shallow event in the end. Okay, so we'll move on from that. We can use that for questions in a bit, but we did mention that statistics, so I want to point out as well. We have been putting some updates on HawaiiTracker.com. Yesterday there was an unofficial statistics post that was put up. And so we had estimated from USGS reports over 415 total events, and the actual number ended up being 478. It's likely due to that 5-hour, 4-hour gap in there that they didn't report on previously. So 478 earthquakes, depth range. We've mentioned that the largest magnitude of the whole sequence was a 3.4 that occurred 1:30 a.m. That first night to the 24th. Right? So the sequence begins at 4:30 p.m. on the 23rd, intensifies. Largest earthquake at 1:30 a.m. On the 24th. It peaks more than 12 hours later, on 7 to 8 p.m. on the 24th, at 28 earthquakes per hour. And the average rate ends up being actually around 12 per hour with that new number the USGS gave us for the total right there. Right, so we can look at this a little more. There's the Iris browser, and maybe I'll just switch to that at this point. We'll look at the Iris browser here, and we'll add the element of time and how this actually occurred. So let me animate it first here. Down here you can see the histogram. So the earthquakes, how many earthquake counts per time. It really peaked right there. That was at highest 28 per hour right in there. And then afterwards it tailed off pretty quick, and here we are with hardly any blue at this end of the graph, showing that it really slowed down, hardly any earthquakes happening anymore. So I can zoom it in for you guys a bit. Let you see how the sequence progresses a little. Got a little render, listen. Artifact in there, that's all right. You see that burst? And one thing that I wanted to point out here, if we look at this when it loops back around, is it actually begins right in here. And then it spreads over this way. And it spreads over this way. But it, as you see it loop, there's a core of it that starts off right there and works its way from there, which is interesting because this is actually over this South Caldera Reservoir area right through there, right? This is a Kīlauea crater right over here, which is easy to pick out in maps often. Kīlauea crater is over here. Maunaloa is this crater over here. So as we orient on various maps, those are our landmarks to reference. And it's thought that there's a Kīlauea reservoir somewhere underneath here, and there's a South Caldera reservoir that essentially comes off in this direction from it, somewhere in there. So very near that core is where it actually begins. So this earthquake sequence, the pressure that breaks, it actually comes up here. We don't see it coming anywhere near Maunaloa. It does respond, but really it's originating over here, which begs the question, and I don't have an answer. We'll wait for the USGS to chime in, of whether this was fed directly from that South Caldera reservoir, which it may have been if it begins right here and then comes up above it and then spreads to this sill-like zone over here as well. So we'll see how that plays out as we hear more research results. So focusing just on that swarm area and excluding a little bit of this stuff on the outside of it, I was interested to look at the time depth plot from the USGS monitoring page. So here it is for the last week or so. Right? So you can see it looks like there's nothing happening over here. This is a background rate of a couple earthquakes here, there, and then the sequence begins right here, and this is basically it right here. And you can see this over, and now we still have some events a little bit on the shallower side, but there's a big gap, and they're not happening at the same rate they were before. You can also, zoom it in here. You could also see this gap in depth. It's a small gap in depth, something that I don't know if I mentioned this when we were talking during our update on Tuesday, but it was noticeable early on. This gap, right? So you have particular bands of time where different pulses coming through. There's a little bit of lining up this way just because of the rounding, right? You can't have a magnitude 1.75, for example, plot on here. So, or I'm sorry, a depth of 1.75. It goes 1.7 or 1.8. So you get a little bit of striping happening in this direction. That's artificial. But when you see it coming up in this way, that's more. We do have resolution and time, and that is more meaningful to see that, right? So something like this that tips to the right. You see earthquakes getting shallower as time goes on. That's interesting. Earthquakes getting shallower as time goes on. That's interesting. So little pulses within that, right? Something like that, but not always so clean, right? Depending on how you look, you might be able to draw arrows going the opposite way, right? And you might have activation of something moving in the middle and it propagating up and down at the same time. So it's not always so simple as that. And you can have adjustments, and those are just the things that people look for as those clear-cut case examples. So that is the time depth for the past week. We can zoom in. I captured this one during the sequence. So this is giving us a little bit better resolution for, if I zoom out here, it says 24 hours, the whole thing. So this is where it began, and haven't quite got to the end there, but you can see that the gap isn't quite as visible, but there's a little bit of that gap in depth right through there. And you can see that there's no order, right? We can see that the deeper area does seem to start off first. That's that beginning pulse right there. And then we see that shallower one activate. But then they basically go off at the same time, right? You see a lot more constant on this deeper dike segment of the intrusion, and more periodic, episodic in this shallower part here, right? At least in this early going, right? So it really seems like this is the source down here, and then this is the consequence of coming from deeper to shallower, perhaps. And we already pointed out the orientation difference. So that's zooming in. We're going to zoom out as well. But first, we'll look at this cross section by USGS from Poland et al. And professional paper 1801 right here. And so it's a little bit different because they mark 0 as being the surface of the Earth. So this is now technically a -1 that we were looking at before, more or less. And this would be sea level, and this would be 1 below and 2 below and all that. So in any case, it's often described in this manner, that below the surface of the Earth, that South Caldera Reservoir is roughly between 3 and 5 kilometers down. So more or less in that zone right in there. And so if we put it as at sea level, then it would be between 2 and 4. So our earthquakes that are happening, they're happening really between 1 and 3, right, with that little gap in there. But we really had 2 to 3, pretty constant, and then that little stripe of around 1. Right? This is all projected and flattened on here. The point being that if we're in this zone right here, then that is pretty close, this area right above that South Caldera chamber right there. So it is nearby enough that it wouldn't be crazy to imagine that it could go from right there to straight above it, breaking through some crack, forcing its way, opening a crack and pushing its way through to relieve all that pressure. So that's how that fits into here. Right? And the other thing to point out here is that we do have a connection from the South Caldera chamber to the seismic southwest rift over here, and that occurs down at around 3 kilometers, more or less, right? Whereas the volcanic southwest rift, the area of shallower cracks, that's more in a zone of 1 kilometer or so. And so that's something we can come back to here in a minute. And why everything is projected cut across on this thing like the Halema'u shallow reservoir is directly above the South Caldera reservoir right here. This is worth showing you guys just so we can look at some of the pitfalls of looking at these projections that are only one view or the other. So here's the map view, and you can see that the Halema'u chamber is offset to the north. The South Caldera chamber is actually offset to the south. The Kīlauea to the side, and volcanic southwest rift and seismic southwest rift are actually offset in map view in a northwest southeast direction there, right? Whereas if you look on here, that is not quite so obvious there. So that's why these projections, you really have to look at all the different views from above and both sides to try to imagine in your head a 3D, and not always so easy, but that's the Kīlauea, and there is the South Caldera Reservoir in map view right over there, and that's the area I was pointing to where those earthquakes began, right through there. Okay, so this is continuing our deep dive. Show you guys what the past month earthquake pattern looked like. So as we imagine that plumbing system of the volcano, you really can see this whole summit caldera area activating with earthquakes over the last month. We saw the seismic southwest rift activating. We saw the upper east rift zone / east rift connector activating. We saw the middle east rift to Pu'u'o activating as well, all to there, right? And of course the south flank with all of its seaward movement, right, as magma is moving through all these other pathways up above. So that's last month, and to focus in on the last month time depth plot here, our event is this skinny thing right over here now because it only lasted essentially 2 days. But you can see that we have had swarms in that area, right? We had elevated activity. This is, maybe elevated a little bit, but not really going crazy. We did have a couple of pulses on the 5th and then on the 8th through the 11th right here that really had quite a bit of activity in those regions as well. So not exactly the same thing. We didn't detect the same numbers of earthquakes, but we certainly were building towards it. We could tell a couple weeks ago when this was going on. Just worth reminding ourselves that was something we saw coming. And then the actual map for the week now automatically generated. Here it is. So here's that plot. You see really absent, no activity in the upper east rift zone, east rift connector, middle east rift, very quiet as well. A couple of little events, but really not anything compared to before. The south flank is still showing that fairly low level, but still showing quite a bit of seismicity. You can see it's still moving. And we do still have some of these blue ones are the deep earthquakes that are thought to be part of this deeper magma pathway into the volcano from depth. And so that's cool, but still happening. It's been happening for a while, so we know that magma is moving through from the deeper to the shallower part still. But that's not something we worry about, as we can't really tie that to any point in time that something's happening, only that we know. Magma is still coming in, so long-term in the volcano, I would expect to resume its inflation and to resume what it was doing before is the temporary relief that we got, and so maybe we bought ourselves a few weeks, perhaps, a few days, perhaps, it's hard to imagine that it's going to be done for very long, really. So, okay, that's the last week here, and there are still earthquakes happening in Pahala. You see these deep earthquakes, maybe not quite as many as before. There did seem to be a little bit of a slowdown, but they are still happening as well in that area, right? And not just the deep ones. You see these yellow ones in the area here. These are the shallower ones above that deep earthquake zone, and there's a big gap in between. You're really not seeing any oranges in between, right? You see just the blue to yellow, right? If we look at this plot here, there's our blues, and there's our yellow, right? No green, I guess is right? No green right there. So there's a gap, and these deep earthquakes don't really connect to the shallow earthquakes. They're basically pushing up, and there's adjustment above it. But there's not a pathway of magma that we have to worry about this bursting through, at least unless we see different patterns of earthquakes, which we have not seen thus far, and ever really, since we've had a seismic network up monitoring this volcano. All right, so it's interesting to look at this pattern for the last week. Most of the event was actually closer to the South Caldera Reservoir. It did cross that boundary. Maybe there's another one of these maps I can pull back up. Look at this one. You can see this shaded relief. We see a little bit of this buried outer caldera fault there, and there's a little bit of a notch right here because this is an interesting junction zone right there, right? So right near that notch zone right there. Is where this came out, but we actually see we're crossing that caldera boundary to outside this outer caldera fault, right? That's the relative positioning of that. Right, so if I go back to where was I? Right here, we're going to talk about how this fits in the southwest rift connector, because here's this outermost caldera faults on this map by Swanson et al. Swanson and Dick Fisk and Carl Thornburg and Mike Poland, 2018, about the Kauai fault zone. Come back. And so there's the outermost caldera fault, and you can see that it does cross through there as well, and then has that pattern bending to the southwest there, right? So this is an area that could have magma going through it and can express seismically, but there's also an area above it that could react that's shallower than that. So the southwest rift connector is down at 3 kilometers, and to show you guys this, I'm going to bring up this paper by Matoza et al. That is cataloging all the earthquakes in a whole catalog essentially forever. So we can see here what this looks like. The whole catalog is showing us this southwest rift. Let's change my color here. There is that southwest rift zone right there. You can see how there's been an expression of earthquakes for a while there. There's an upper east rift zone comparison. Right? Very clear features in there, and then our summit area, all of that, right? So Once again, we're going to project down. This is our cross section, and if I scroll over, you can see this is a 1 to 5 kilometers down. Once again, there's a deeper one right below here. We're going to ignore this lower one because everything is squished in. But our southwest rift is, let's get it zoomed in as it possibly will go. I think this might be it there. It's down from here down to here. It's actually this little guy right in here. That's a seismic southwest rift, right? So you can see going over maybe 2 kilometers, 3 kilometers. That's the area we're looking at right through there, right? So it's not quite where we are. And if we look at the earthquakes that we just had, we were up shallower than that, right up in here, 0 to 2. And so we're in an area above that, and not on the seismic southwest rift itself, right? And this is something the USGS referenced in one of their updates, is that the southwest rift was not showing any sign of magma activity, despite it being very near that junction zone right there. So that's the east-west view. If we look at the north-south cross-section over here, it's not as interesting as far as the southwest itself. You can see that really the summit zone sits to the north of both of them, and actually the upper east rift zone and the southwest rift zone, you can see, are offset. The southwest rift is shallower, and the east rift zone is deeper right there, right? Maybe you can see it a little easier on this bottom one right here, a little shallower and a little deeper. But even still, all of our earthquakes, everything's happening in this zone over here, right? Maybe like that and kind of into there as well. So in the end, the southwest rift does not seem to activate. Here are some plots of what this actually can look like when the southwest rift does activate. These are earthquake plots from Intrusions over time, for paper 1801, pulling it all once again. So this is 75 to 76. This is after there was the big earthquake in Kalapana in 1975 in November. So following that, the south flank was still moving. South flank goes all the way off this way, and there's that interesting that way, right? The interesting point is that apex junction point, this triangle zone of the Klauea, that's where we're activating it right through there. And that's why this is interesting to talk about where it might go from there. So we activated in this event just up here. We didn't get anything past that. You can see over here, this is the most dramatic one we had in 75, 76, where we had an injection, an intrusion all the way into the southwest rift, all the way down to here, right? And it seems like likely, you see all these blues, this is all that south flank décollement zone, the south flank getting pushed out from the magma going into it. That's probably as dramatic as it gets right there as far as earthquake patterns goes. So something a little bit less intense, 1981. You see similar summit sequence, that connector zone right through there, and propagating all the way out again, once again over through here. And a little bit of south flank action, not nearly as much. Didn't go quite as far down, you can tell, right? That's 81. 82. You see clearly went down, and a lot of south flank movement. These deeper blue ones over here, and it looks like we had magma movement perhaps, or at least shallow effects all the way down here, the southwest. And in 2006, more recently, you can see seismic southwest rift, and perhaps something moving as far as there, right? You know, just because you don't see earthquakes in between doesn't mean that magma is not moving there necessarily. It just means it can move there without actually pushing any rock apart. Maybe the cracks sitting there open. And there are lots of big cracks in this area all over the place, right? This is all south flank that can move. There haven't been as frequent eruptions in this area, so there's a lot more cracks that haven't been buried or are still exposed, for example. The 1868 earthquake was epicentered over here, more or less. So that was the one that was a 7.9 that caused huge movement of the ground. So there's all kinds of cracks all through here as well, and that's the kind of thing that can happen. But we didn't see anything like that. We haven't seen any earthquakes anywhere past this zone right here, and that's the noteworthy point. This is just a point of comparison of what it might have looked like if we had seen more southwest rift action. Okay, so let's keep going and finish up the earthquakes before we look at the rest of the monitoring signals, then turn to some questions. Earthquake rates in depth for the past month. Here is our winter day right there. Let's zoom it in for you guys. Right there. This tick mark right here, I believe, is 350. 350 earthquakes per day is what we exceeded on that one day based on this particular bucketing interval. Right? So we saw 350. This is every 50, so that's 300, 250, 200. So together, 150 perhaps plus 350, or no, what is that? Yeah, 150 plus 350. And then over here, that is closer to 100 or so. That's 600-ish. We're talking about across the whole volcano. This automatic plot is the one that captures all the deep ones and Pahala as well. So it's interesting to see what it looks like on just, arbitrary buckets. Overall, we heard from USGS, 478 is the actual number for one for the full sequence over the full 40 hours or so, 40 and a half hours perhaps, depending how you cut it off. So past month, that's how it looks. Past year, earthquakes per week is our plot over here now. We're at 1,000 at the top, 0 at the bottom over here. And here we actually are topping 800 earthquakes per week, right? Which is not a surprise, because if I come back to, where is it? Oh, that's the month. Come back to this plot, weekly earthquakes. Our number up here actually says 978 earthquakes for the week that this map is actually capturing, right? So as we haven't quite got to a full week here yet, that's why this bar is a little skinnier in the right here. As we fill out the rest of this bar, it may still climb and we may get up quite a bit higher still. Right, we'll see how far we go. 978 would be all the way up to here, right? If that were the actual bucket that it catches, and so we'll see if it gets there or not. You can see this is clearly a jump above this other background we've had before. This is what we've been talking about for a few months now. We're looking for that jump as the indicator, and that was it. It was obvious when it happened. That's kind of what it looks like. And that corresponds similarly to what we're seeing in the time before the 2020 eruption, right, where we had elevated background as well. This was the events that happened in Namakani Payo, adjustments between Kīlauea and Maunaloa as well. Here was our intrusion that occurred back in the end of November, early December 2020, about 2.5 weeks ahead of the actual eruption. And you can see that after that occurred, there were earthquakes elevated for a while still, right, for those 2 weeks before it actually popped out. So we'll see what kind of pattern we get if we have a spike that goes up to 1,000 and drops way back down again, or if we end up with these elevated, perhaps 700-ish earthquakes per week level. That might lead to something else in a few weeks, right? Because as of right now, we can say that this event that has not led to an eruption, at least in the short term, it's only been a day, of course. It could still lead to an eruption in a longer term, but that is to be determined, and we'll look for signs, things like this, to maybe give us a hint or help us have educated guesses to what might actually happen. And these are just guesses, of course. It's nature. She'll do what she wants to do. That's what we're looking for, comparisons of the patterns, right? That spike up, and here is our parallel, our spike up right here. So very interesting to see that finally happen. We've been talking about it for a while, and there it is. So a few more things here. Here is that map of that intrusion, December 2nd, 2020. And you can see that earthquake pattern that they had at that point was certainly interesting and had magnitude 3s as well, similar in size. But clearly it did not have that tail that went off to the south. That's not what we saw then. That's certainly different from then to now, right? Clearly it was focused more in the Hale Ma'u and upper caldera and the central caldera area. And in the end, they decided that the best fit models were an intrusion in this area where this green rectangle is, right through here. Okay. That was consistent with these green arrows, which are GPS stations, showing movement away from there. And so that's something we'll look for, and we can get something like this hopefully shared with us. And for all I know, I haven't seen today's Volcano Watch published by the time we started our broadcast, but perhaps they'll put something out like this as well. We'll see if they have. We'll add it in here at the end. All right, so GPS is an interesting thing, and Interestingly, we did have a restoration of the GPS signal in the last couple of days, so that's great. So here is our Uekahuna to crater rim, north to south across Kīlauea caldera distance measurement. And you can see, just for a point of comparison, here's 2020. Here was our intrusion when it climbed way up. And it stabilized a little bit before rising again, and when it erupted, it relieved that pressure to come back down. Right, so that's the 2020 sequence. And the eruption, during eruption, it started to spread again, showing swelling, right? So that was something that's interesting. And it's been swelling ever since. That's the overall pattern. Zooming in closer, you can see that there was a little bit of this, we previously had this little bit of a slowdown and coming up, and at the time this was described as a shifting of the center of inflation slightly to the south. And perhaps because magma is trying to move towards this area where it's intruded now, right? And imagine that as magma is filling areas, if it can find these cracks without having to break anything, you don't have to have all a sequence of earthquakes, all that. You can just go and find these zones and fill areas more passively. It's only when it gets to the pressure where those areas are mostly occupied that it has to break somewhere new. That's what we just saw happen. But it certainly has had these other adjustments before, shifting centers of inflation to the north right here. And perhaps that's what happened here recently as well. It's hard to tell. We'll have to wait for the USGS to tell if that's what actually happened right here, within the last month or so. That little drop down right there before it came back up. And then it looks like the eruption itself, not the eruption, the intrusion, pardon me, in the last couple of days. Well, looks like before that, actually, it was already flattening out, maybe maxed out, and then we'll see what happens here. We have a slight relief as well, but I would not be surprised to see this continuing to rise in the future after whatever adjustments we see here in the short term. Once again, we'll wait and see. That is the summit signal in GPS for Pu'o'o. Important to note, our scale is still very, very small. We're looking at a 0.5 centimeter scale here, and still not really a whole lot of change. It's wiggling around within this range of variation that it's shown. So nothing really to speak of. No effect on the East Rift, Middle East Rift, Lower East Rift. All safe. All this activity has all been an international park away from people. No threat to people, no threat to communities, habitations, infrastructure, any of that stuff. It's an area of the park that's actually closed. People can't get there very easily already anyways. So it would have been fine if lava had come out of the ground there as well. In fact, that's a great place for it to go because there's no people there, or it's a lava landscape. That's kind of where it belongs. Yeah. So that's our GPS. We're going to scroll back up here in our USGS HVO deformation page and look at our tilt. Let's go all the way to the top, right? And just in case any of you guys haven't ever seen this before, that GPS distance measurement is measuring this distance here between these two blue boxes right there, right? That's the length we're measuring that we just described at the summit. And then at Pu'o'o, we're looking at the length right there, essentially, going across the rift zone right there. So all the action is up here. And we'll look at the tilt meter, Uekahuna right up there. That's this blue one. And what you can see is that we're coming out of what appears to be a deflation-inflation cycle in the last couple of days here. We really can't see a whole lot. Our scale is 2.5 microradians, not that much. So for the past week, that's this right over here. We can see our deflation-inflation right through there. The event occurred from the 23rd, about 4:30 p.m., maybe in here or so, to the morning of the 25th, maybe in here or so, something like that. So that's the period of the actual intrusion. It's not of the same magnitude as the deflation-inflation or a lot of other stuff happening in this graph. So really the signal was not very strong at Uekahuna, is the bottom line here, right? Maybe this is a signal. You can certainly see all these earthquakes putting up little extra wiggles, little extra blue spikes on this thing. But especially if we zoom out to the last month, here's our last month showing our inflationary trend prior to this, and then this deflation-inflation kind of patterns that we see. Right, and here is the last intrusion sequence right here. That little thing. Really small compared to what we've seen before, even compared to deflation-inflation that we're just seeing right now. Right. So interesting. Maybe if we want to microanalyze this, we can see there's a little bit extra wiggle through here. Maybe this is indicative of quicker changing, shallower processes going on, but this may not always be the case. This is hard to go further from there, in my opinion. So we'll leave that at that for at least for today. Okay, that's our tilt.
I thought we were going into questions and stuff like that. Sorry.
Okay, so there is a better tilt, which is a sand hill station right here. And this is a whole different scale, microradians from 50 to minus 30. I mean, we have 10 microradians per hash bar with an 80 microradian scale all the way up to altogether. Right? So that's a huge, huge scale. That's the kind of thing that we're looking for as a signal of near surface changes. And once again, we have two lines. There's a blue and a green, and we're going to talk about this in a little more detail today, since this is our deep dive. It's now or never. We probably won't talk about this ever again. So here is blue line, green line. These are two different azimuths of direction, right? 226 and 316. More on this in a second. These are often described as a radial and tangential tilt vectors, right? And that's something I'll get into in a second as well. But essentially, two different directions are like at right angles to each other. And you can see that they're both showing signals. The green signal, this tangential, is showing a much stronger signal, much larger magnitude of deformation than the blue radial signal right there. Right, they're both showing a lot of these wiggles, big earthquake jolts. Right, the instruments moving really far, then moving all the way back to where it started, and then resuming its trend. Right, so it's not offset. It's just a jolted, and then it comes back to where it was before. And that's something that's really hard to, when we have a tilt plot that updates only every 15 minutes or so, it's hard to tell what's going on, you know, where that line goes next when we're trying to monitor it in real time. But definitely interesting to see that, right? So to dive into this a little bit more, we'll also, a couple other things first, right? You know, you can see that the tilt was fairly flat, and it's been fairly flat after the event on both vectors, right? So that's all interesting. And we'll see what this actually means here by first looking at the location. Location is the most important thing here. Let's see if I can get this monitoring map to show on our live. It is usually not very well behaved. But all right. Looks like it's going to work. I have on here, the triangles are the seismometers, and this little red bars are the tilt meters. So we're going to zoom in way into here because, oh, too far. Here's our shallower flat spot, and here's our deeper skinny and tall spot right there, right? Our station happens to be right here. It's almost like at the center of an arc, right? It's like a radius that moves around, right? So very interesting to see that the station happens to be a very unique location relative to this activity. So I'm going to jump back to here, and we're going to show you guys how this actually works. So in this case, the radial tilt is set up to be at an azimuth of 226, and the tangential tilt is set up to be at 90 degrees off at 316, right? So 226, let's look at that. And the way this works, in case it's not familiar to you, is here's a compass rose with the azimuth direction. North is 0, we go around clockwise. So east is 90, south is 180, west is 270, right? So when we see here, we see 226. 226 falls right here. That's technically southwest, right? But this is like a seesaw. It's actually azimuth that goes all the way across southwest and northeast like that, right? That's our axis that we're looking at. So if it goes down in one direction, it goes up on the other by definition. So they're basically linked, right? Kind of the same thing. And this is set up such that if there's inflation from that point source in this direction, they're saying the point source is to the northeast, right? So if we come back to our map, what's northeast of this station? It's Halema'uma'u. The Halema'uma'u Reservoir is what's northeast of the station. That's what this thing is set up to actually monitor radially, right? And tangential to that, if that was the only point source, then yes, this other direction would be tangential, right? But as it turns out, because we have this arc of activity around this, our northeast direction is picking up this shallower, flatter zone in our southeast direction is picking up this taller, skinnier zone. Just by chance, we happen to have one tilt meter in an interesting location right there, right? When we look at the one at Uikahuna, that's all the way over here. So it's not showing as strong a signal. What's not surprising, it's not right over the intrusion like this one at Sand Hill actually is. Right? That's really the one of the keys to this whole thing, right? You can see the seismometers as well. This seismometer over here is the outlet digital, and had some crazy variations. It was like the whole instrument was getting shaken and getting set off of level, and in fact now is offline as we speak. So maybe even the antenna got wiggled enough where it's not sending data back in the right direction. So certainly you can have failure of stations if they're right in the area. So this one's just right, just off to the side and picking up something from the northeast and to the southeast. So it's not exactly appropriate now to call this radio and tangential because we no longer have a point source. Right? We actually have two different sources of a very complicated geometry here and here. And that's why we might see, now coming back to this, it's why we might see the one to the northeast, the smaller, shallower one, showing a smaller signal, and the one to the southeast, the deeper, taller one, larger one, showing that larger signal right there. Right? Not that surprising when you dig into the details of what's going on there. And as far as what it does next, right? Because this is so near that station, I wouldn't expect it to go back down at all. I think that's the thing that said that that's an offset. The ground is now taller there because now there's more magma sitting in there until it cools off and hardens, right? That's not going to change. It's not, unless it drains off somewhere for some reason of something else happening. No indications of that happening. So I would expect this to stay as it is now and perhaps resume its inflationary trend in the long term, right? Something like that. Because if we come back over here, we can see that was a long-term trend of this station, was a slow inflationary rise. Right? It's kind of blown out of proportion with the scaling now because we have such a huge signal here, right? 10, 20, 30, almost 40 microradians. Is that correct? Yeah. So big changes in tilt, and not surprising given that location. All right, so what else? Gas data. We don't have any manual measurements, but no gas has been detected, anything different like that. We have had reports of people smelling more gas in the volcano area in the last week or so, but we've had southern winds as well and some different weather patterns. So really it's the same gas coming out. Even 50 tons per day is a lot. If that was a factory, they'd get fined. Right, but for volcano, that's what we call just a little bit, low levels. But still, if the wind blows the wrong direction, you can certainly smell it. It'd be like having a factory a mile away. Yeah, putting out more SO2 than it's supposed to, even according to their EPA regulations. So we do have this ambient air SO2 concentrations. A couple of these signals are online right here, and you can see really no change in natural variations that occur. Right, similar thing, wind direction changes and all that. But think of the baseline, perhaps, really hasn't changed. It really hasn't changed at all. So really no SO2 to speak of. And is there anything else on this page? This is our, oh yeah, we're going to come back up here. We're going to look at, this is one last interesting thing here on Kīlauea. When we look at this lava lake depth, this natural rangefinder, for a while we've seen this daily up and down cycle, and it's been I'm kind of curious if that was something that had to do with temperature or if it was like a degassing or what it might actually be. What's really fascinating is that here, during this event, that pattern was much, much more dampened. Maybe it happened, and if so, it was much smaller, but it may have not happened at all potentially, right? That's something that, that is very, very curious. And if let me see, I'm going to go back to the past week here and show you guys that plot, right? Right, there it is. So here's the 23rd to the 25th right there. And you can see that after that intrusion wound down, that this pattern picked back up again. It's ongoing again now. So very, very curious. I'm not quite sure what that is yet. I don't know if it's something like a deflation inflation kind of, like a gas pistoning kind of thing from perhaps within that cooling lava lake. And maybe when that swarm was happening, it was not allowing that process. It was disrupting that process, and maybe allowing the pressure to not build in the same way because it was being diverted elsewhere. Speculation, but interesting to consider what that might be. This is our first indication that this might actually be some physical process tied to the magma, in fact, right? And likely the gas as well. But that's what we see here. And once again, I'll await hopefully something fascinating written by the USGS about what the heck is going on here. Why did that stop doing that, right? Maybe, like I said, maybe you see a little bit of signal here, maybe a little bit. It's good ones to do it, but really it didn't happen there, right? And maybe there is something to do with the temperature allowing the gas to I'm not sure, if there's something that actually triggers the cycle to occur. If that's something atmospheric, I really have no idea there, but it's interesting to consider those things there. Last thing for Kīlauea there, and so we kind of look at the F1 thermal camera. No changes. These brighter spots are those what I'm calling chimneys of heat and gas coming out from that still liquid lava core inside of that hardened lava lake. Okay, so one thing that I found out that I'd bring up today, since it's relevant, and let me come back here and let's go back to this last month of the lava lake depth, because we did see these interesting little wiggles in a lava lake surface, and we did say that possibly that might act like a sort of tilt meter in the long term for us, showing if the ground is moving around, right? And so I think we did see that. I think we saw these little wiggles coming back to the about a month ago, or even, right, when we started seeing the pressurization of the system, maybe some tilting and effects on the surface of the lava lake, right? And to the point where it looks like it was actually rising here, right? Like it was getting lifted up higher. So very interesting. And then that more recent pattern right over here of the overturning, right? So if it's tilting around and getting pushed upwards, can lava break out of there? That's a natural question that I'm going to anticipate before anyone even asks it, and show you guys this graph. This is a graph of Kīlauea as it was cooling, and this is depth on the left, and this is time. I just have the first 2 years here because that's what we really care about when I have to look at the whole 35-year history of Kīlauea. But what you can see here is that the first few months here, the crust was forming at 3.9 feet per month. And then it slows to 1.8 feet per month, and eventually about 1 foot per month. You can see that the thickness rate of growth decreases over time, right? But if we say, okay, it's been 3 months since that eruption, and we're to look at an analog, right? And of course, our lava lake is thicker than Kīlauea's, so maybe it's a little bit different. But for Kīlauea comparison, after 3 months, Kīlauea was in the order of 12 feet thick of crust or so, right? So that's to say that we may have something in the order of, maybe it's not 12, maybe it's 8, maybe it's 6, but, somewhere in that range of, it's not like a few inches. It's many feet of thickened crust, and that's how come it's been able to stay intact through all the tilting and all the earthquakes and all that, right? Because it certainly is possible at any time in the future that liquid core gets squeezed out of there and pops out of there as well. That did not happen this time, and perhaps this is because of this growth of the crust here. And as you can see, as time goes on, it gets harder and harder and harder to do that. It takes more and more pressure to break through that thicker and thicker crust. So just something I'd throw in here for that question that's going to come up. So here's our view of the summit. No glow, no lava. Looks the same as before. I thought I'd give you guys this view just so you can revisit what the critter looks like. And we do have a panorama from the tower of that southern area right in here. Against that back caldera wall is where all those earthquakes were happening. And so imagine that shallower section was something like this from this angle. This this kind of orientation, but probably deeper down there somewhere. And then the deeper dike would have had an orientation like this, and going in and out of this photograph, like that, into that area right there. Right? That's the zone that we're talking about. So really quick, there's not a whole lot happening in Mauna Loa. We are going to get to some questions here, but I just wanted to show you guys nothing changing in the tilt, nothing changing in the GPS. Our earthquakes, 43, just a summit and south upper flanks, not a whole lot different there as well. Here is a map of them, same areas last week. Last month, very, very similar. Last year, earthquake rates were still way down. Not a whole lot has changed. And as I alluded to earlier, we'll not be surprised to see Mauna Loa's alert level dropped down as well anytime now. Anytime. Now that we know that they have a mechanism to change this quickly, they can decide to change it and change it quickly. Right? So we'll wait what comes next on that. And just one last thing here. What's that?
The idea that it's getting lost in the bureaucracy, the changes, no longer applies, basically. Like they've shown that they're able to move quickly, even through the paperwork or whatever is necessary to make those changes at the federal level. Yeah,
that's great. That's great. They're more efficient. They've improved. Great to see that. Yeah, fantastic. So yeah, one last thing, which is the Volcano Watch. We did not get to it last week because it was a late publication as well. I just want to mention very quickly, I'm not going to go through it all. We've talked about Aila'au lava flow before. That was a topic of the Volcano Watch last week. A couple of things to mention that are interesting here. The Nahuku lava tube, Thurston lava tube. There's this other more used name in previous decades as part of that whole sequence. It was a 60-year eruption, and they think 166 square miles of land covered over 60 years. For comparison, 2018 was less than 1/10 of that area, and Pu'o'o, that was longer lived, about 1/3 of that area. So it was a really big, long eruption. I'm going to switch over to show you guys this map right now. This is the map of the lava flows. The shield area being up here. Looks like I need to go to yellow. There is a shield area, and most of the flows going off to the east, right? So I thought that this shield acted as a barrier, right? So no lava goes this way. It does spill to the south, and mostly to the east. Right? And imagine this is a big ridge that rift zone as well. So how to get across a rift zone there? That's pretty fascinating that it was able to do that, and just one trickle going down across, and then otherwise it's split across. Right? So very long flows. You can see all the way to the ocean. It covers most of the subdivisions that people live in this area that are mentioned on here. So as I mentioned in the article, Maunaloa Estates, Fern Acres, Fern Forest, Hawaiian Acres, Mountain View, Orchid Lands, Hawaiian Paradise Park, Ainaloa, and much of Hawaiian beaches are all on the Aila'au lava flows. Also Kaha'olea Natural Area Reserve, Puna Forest Reserve, all of that. One thing which is a little bit confusing, if you have come in and seen our talks about the history of Hawaiian stories of Pele, for example, this corresponds to the Pele Hi'iaka story, not to the deity of Aila'au, which is referenced in the new name of Fisher 8 from 2018, Ahu Aila'au, right? The Aila'au deity, which existed prior to that is what actually built what's called the observatory shield area. That's what Aila'au, the deity, did. And Pele, the deity, battling Hi'iaka, makes this Aila'au lava flow. A little confusing, named before we got this nuance quite right. All right, so just a little point right there. They do mention there are lava tubes besides the Thurston, Nahuku, like the Kazamura. The Kazamura, that is the longest continuous known lava tube in the world. Right? A lot of qualifiers, could be some unknown. There are some longer ones, really long ones in Australia. Collapsed, no longer continuous. But this one also has the distinction of having its entrance close to the summit of Kīlauea, perhaps, not quite 4,000 feet elevation, but, close. And dropping down to close to sea level, maybe 100 feet above sea level. So that means that it actually drops down 3,600 feet, 1,100 meters largest vertical drop of any lava tube, and it makes it the deepest cave per se by that strange definition as well, right? 25 miles of one straight passageway. If you map all the various levels of lava tubes and splits and all that, you actually are 44 miles of passage in the Kazamura cave, and we can do that in more detail in a future some other time there.
And before anybody asks, no, you cannot walk the entire duration of it. Like, it goes through a bunch of private property, and I know guys that have put fences up down there, in the cave to keep people from traversing it, because a whole bunch of drama happened because of those things. Like, thieves were using the caves and using it to sneak around and stuff like that. So you're not gonna be able to walk it, basically.
There's all kinds of
it's still there.
Weird, interesting stories about these things. Some people use them as wine cellars because it's temperature regulated. Some people use them as a cesspool, right? So it actually was surveyed at least once, top to bottom, and I want to say it took the people 3 days to go from top to the bottom, mapping the whole thing out, right? Through all the whatever is down there. Yeah.
Right.
So it is mapped.
Would have been easier in the past to do that. For sure.
Certainly, yeah. So, while I have you, Dan, is there any new Volcano Watch published
Nope.
for this week yet? No?
Nope. Nothing.
All right, so we'll wait that, yeah. Maybe taking some more time to talk about the event this week, and we will bring that to you guys next week as we follow up on what happened here. So, that's here's a map of the Kazamura, a little piece of it. There's all kinds of cool things in there. This is the Wonderland maze, right? Hard to see some of these photographs, but very, very blurry, right? A person standing in upper level, upper passage, lower passages. People coming out of a lava tube over lava falls that drops down into a giant plunge pool. All this 60, 80 feet underground. And so some really cool stuff there, and we'll save Kazamura for a special talk of its own someday here in the future. With that, we can just let you guys know that we're brought to you by HawaiiTracker.com, where we're posting updates more frequently. So if you're interested in what the Volcano Watch is, you can come up and check it out when it gets published. Dan, you can see posted earlier today about the lowering of the alert level, and all that's all the other things as well that we've put in between. So, right. Dane, who else?
That is where we do all of our tech stuff. So if you want a different medium other than the video, that's where we do all of our text-based publications. We put our links to all of our videos there as well. We do have a bunch of thank yous to get through, so I want to get through those real quick. We had some super chats. I really appreciate those. The first one was from Darren A. He says, mahalo for all the great information you provide. Appreciate that, Darren.
Darren.
Second one was from Tim H., who donated $5 and said $40. And then Tim H. donated $40. So we appreciate that one, Tim. Appreciate you taking the time to get that figured out. We also have a couple sponsors that want to thank them as well. We have Kaleo's Bar and Grill in the heart of Pahoa. They do some unique twists on some more traditional dishes, a little bit of local flair in there too. Indoor, outdoor dining. They got takeout options, so all that COVID-safe policies. Really good food, competitive prices. I like to go in there pretty regularly. Really good place, so we appreciate them. Kaleo's Bar and Grill. If you're in Boa, check them out. Second one is Kalani Tours out of Kona, and they do a few different kinds of tours: volcano tours, waterfall tours, some Kona coffee farm tours. And they have a few other ones that they're looking to be adding. They do very small tour groups, so you get a little bit more knowledge from the tour guides as opposed to being shuffled around in one of the big shuttle buses. This is more of that intimate knowledge. It kind of gives you that little bit of knowing more about the context of the areas that you're going to see. So we appreciate both of our sponsors. We also are brought to you by a grant from the Hawaii Community Foundation through the County of Hawaii, the Puna Strong Grant. So we appreciate them as well, everybody that makes this possible. If you do want to help this channel grow, you enjoy this type of content, best thing you can do is like, subscribe, consider sharing this video. really helps out a bunch. We do take monetary donations on hawaiitracker.com/support if you are so inclined. So now that we're through that, let's get into some questions, huh?
Yeah.
We got a couple here that we've done before, but let's do some that are focused on what we were just talking about. Tarzan was asking about the earthquakes sequence over the past 72 hours, but focused on the 0.2, I think it was a 2.3 earthquake, 0.2 kilometers depth last night near the summit area of Kīlauea, and what that kind of shallow earthquake amongst all these other more deep earthquakes might mean.
Yeah, let me pull up the earthquake map here. And, okay, so he's saying 0.2 deep earthquake. Maybe that's in miles. I'm not sure. Mine is in kilometers at the moment.
Yeah, I'm not sure.
Could change it, but I do see here there's 0.4 kilometers. I see a minus 0.1 kilometers, which means above sea level. There's a 0, so a minus 0.1. So there definitely are those shallow ones there, right? And essentially is that if you have something adjusting below, then anything above it could adjust as well, right? Like the Earth is layered with all these lava flows that have natural fracture planes between the flows, normally speaking, right? That's how most rock layers actually are. That's one of the directions of fractures between the different layers of rock, right? So if you imagine having a whole stack of layers, like a stack of magazines, for example, right, and you start wiggling the ones in the bottom or bending the ones in the bottom, it's not unheard of for one of the ones at the top or ones at the very, very top that have the loosest and the most wiggle room to also wiggle a little bit as well. And especially if you're deforming everything below that, anything above that is all fair game to deform as well too. So I see those shallow ones, and so long as I don't see them actually migrating from deep to shallow in a definite pattern over time, then I am less concerned that it's actually like injection of magma in that direction, right? More so an adjustment overlying an area. Although with a caveat I did mention before, you can have magma moving through areas without seismicity too. So you just kind of have to, there's a little bit of an art to recognizing the patterns there for sure.
Okay, Ron K asks, does the pattern of earthquakes indicate magma may erupt in an area different than the lava lake inside Halemaumau or even the caldera itself?
It's hard to say. When we look at, for example, that intrusion sequence back in December 2nd, 2020, that occurred in the south side of the caldera as well. Not quite as far south as this, but when eruption occurred, it pushed back to the north. It's all connected down there. So it could easily pop back into the crater. All it's got to do is find any one of those cracks that leads back into the crater, and boom, it's there. Right, so very easily it could build back towards the crater, right? And in fact, in the crater, it's easier for it to pop out than outside of the crater, and maybe that's why it didn't pop out. And it could certainly, perhaps, if it follows the same pattern as before, it could take 2.5 weeks and pop out back in a crater to the north.
All right, we have a question from Facebook. Kind of question on a lot of people's mind, probably. Is Madame Pele ready to put on a show soon? This user says that they're going to be on island until Sunday.
Well, she's not showing it right now. It looked way more promising 48 hours ago than it does right now, when this thing was peaking. But you never know. It's only a temporary relief of pressure, and as we've seen there's earthquakes happening deep by the deep supply system, and so we think magma is still coming in. It's just a matter of time before it pops again. Now by Sunday, gotta get lucky for it to be pressurized enough for it to come out again that soon. I wouldn't be surprised if it takes a few weeks again, or depending. This sequence was much bigger than the intrusion we had. It seems like it's earthquakes wise, than the one we had back in December. So, did we relieve more pressure perhaps? And if that's the case, will it take longer to build back up to an eruption? That's possible as well. So good luck, Ron. I hope you see it, but I wouldn't bank on it either.
Right. Sharon asks, does the water table have any effect on the caldera now that the lake is refilled and solidified?
That's a great question. We'll discuss it. I don't know the answer to many of these things. I'm just trying to share with you guys the factors involved and what might go into it without really knowing what the actual answer is, right? So we do know that there was the west vent and some path, the whole fissure system, the north vent, west vent, through there, that magma came up and through. And we believe that at least through that pathway coming up, and likely around that cooled pad of lava itself, that groundwater has probably been boiled away, and you probably have one of these so-called steam sleeves or something like that, right? Some kind of buffer zone where the water hasn't quite reoccupied the area because it's still too hot in that area right there, right? So that might be localized, maybe in Halemaumau area, I would guess. Yeah, if I had to guess, all I can do is guess. So it's an interesting question because over here is different, right? So maybe there is still water right above there, and that, if this were to come up, you could have that same pattern, but that's not by itself cause for alarm. Just to reiterate that, every eruption in Hawaii comes up through the groundwater at some point. It's more about the rate it comes up being unusual, and that being something for generating explosions that we might worry about. No signs of that happening. We were more worried about it post 2018 collapse because we'd never seen what happened post a big collapse like that before, and we're past that now.
Right. All right, so I've seen this question a few times, mostly from users that I don't think they've been here for when you previously answered this question. So, gonna go right into it. What do you think about the Helena sump doing some kind of mega tsunami and, destroying half of the Pacific Ocean or whatever the YouTubes is suggesting it might do nowadays? What does this impact anything on the Helena sump, the recent activity, and what is the risk factor of the Helena slump compared to other risk factors that we might know about?
So we will talk about the Helena slump in way more detail someday. I keep putting it off more and more and more, just because I don't want to open the can of worms when there's other things to talk about. So let me get a spot here to drag an image that has a Helena slump cross section on it here. Let's see, do I have this on the screen? Yeah, okay. All right. So this is the south flank of Kīlauea. Kīlauea Summit, Southwest Rift, Helena Fault System. The head scarp is right there, East Rift Zone, right? So they have a couple of lines here, some cross sections go all the way down to here, looking at the foot of this landslide right over there, right? Because there are some big landslides. Here's a Helena slump. It's shown as this upper section right in here, right? And you can see that its block goes down to 3 kilometers down, something like that. And it's actually got a curved fault surface that bends down, it bends up, it bends down, it bends up, right? And that's just this upper part. There's a deeper fault zone, this detachment, the décollement, which is down here. And that's the master fault, really, that everything slides on. So when we talk about a south flank moving, it's this whole stack right here, right? So Helena slump is an upper portion, an upper sliver of that south flank within it right there, right? The whole south flank moves, but as it moves material down towards the front, you can see that these black lines are faults. The faults are actually pointing uphill. This material is going to come and get pushed over this hump. It's kind of piling up. It slid off while the volcano was growing a long time ago, made a big pile at the bottom, and now this is basically like a backstop, right, where everything that comes in here basically makes this big pile higher. You can have little landslides from here to here, generating that kind of landslide block like that, right? That's kind of what you're getting. You can even have little basins that form right in between this outer rise and the inner slump right there, right? So interesting features right there. The point of all this is that it's hard to just by gravity drop this thing out. It's not like it can fall off into nothingness. There's not nothingness for it to fall into. If we're talking about sea level, here's sea level. The water is all above this, right? It's not like there's bottomless ground for it to fall into. It's got to slide to the side, and up this little hill to get over. And that's why this area does not seem very primed for large landslides anytime. Now, this whole idea of large landslides is something I would worry about more so on Maunaloa, and that's something we'll talk about in more detail in the future, the Lika landslides, all that, but not Hila Napali and not Kīlauea per se. And so when we look at the actual depths involved, right, we're looking at earthquakes way up here at these kind of shallower depths. So maybe it could have some effect on a shallower slump, but let's look at the location. Let's go back to our location, maybe here. No, maybe it's not zoomed in enough. Or zoomed out enough, right? Because we can go like that, right? Okay, so here's a headscarp Helena way down here, and here's our earthquake swarm way over here. So we have a good, I don't know, maybe 10 miles in between them, and a lot of other cracks that can accommodate that deformation, right? So long story short, I don't expect any effect on that Helena slump system from here, right? I think more so we see the whole south flank moving, then you might see little adjustments and like little wiggles, and usually it's like, a couple of drops, an inch this way, an inch that way, and not some massive tsunami generating landslide kind of thing, right? That's not something that we that I believe is very likely in this Helena area, right? Even though that's what's popular on the internet. The area I worry about more is Lika over here, this part of the island, Maunaloa, west flank. So we'll leave that to the future. The idea is totally valid. That's what I want to say. The idea is valid, but I think it's valid for a different part of the island than it usually is talked about. And
right.
I'll leave it at
the
that.
Helena slump gets a disproportionate amount of hype to it, considering the risk and what, there's other alternatives you could talk about if you wanted to talk about it.
Yeah, I don't know if it's
really
because Helena is easier to say than Lika, or more memorable, or I don't know, more sexy or what, but like I don't know why Helena is the one everyone talks about and not Lika, because if we just substituted the names, then everything makes perfect sense.
Right,
but
a lot of
the
it
wrong
does,
name.
We're talking about the different spots, and
it's
just not the same thing.
Yeah, different spot,
right.
and certainly different volcano, and that's the key. So this volcano is not going to affect it in that way, we don't believe.
Right. All right. JWS, you showed a figure from Walter 2005 on the Maunaloa cycle. The unclamping seems driven by compression at the base due to flank rise. Is the recent inflation pushing on Maunaloa's flank? I believe that's the recent inflation of Kīlauea.
Yeah, so it's interesting, right? Because Maunaloa showed a lot of inflation earlier in a year, but it has basically been flatlined for a while now. So Maunaloa perhaps is in neutral, and this is important because there's been some speculation that when Maunaloa is inflating, it actually pushes and pinches close a southwest rift and prevents anything from happening there. Right? So that maybe there's something going on with that. But certainly if magma is able to come into the southwest rift, which it really didn't, it was more in a caldera area, but if it were to go on a southwest rift for the sake of discussion here, then it certainly would be pushing back, right? And that's why it might be important that Maunaloa is not inflating, that might be happening a little bit, but maybe neutral is not good enough, and recent inflation maybe, right? And we know Maunaloa's south flank is actually as a whole moving this direction to accommodate that deformation, so that might be offsetting this whole effect as well.
So Ron had another question about earthquakes and the relationship to magma. Like, at what depth would we start to associate earthquakes with magma, and generally speaking, what ones would we not associate directly with magma movement or intrusions?
That's tricky. It really depends where, right? And that's something that we've studied in the past. And so the easiest way to answer your question is to refer to like a graph like this Poland cross-section that shows where we believe the magma is in different areas, right? So, and a reminder that within the actual magma itself, you can't break a liquid, so you can't generate earthquakes in it. It's got to be in the rocks surrounding it. Right, so but you can see if it's in the southwest rift, it might be shallower. It might be down 1 or 2 kilometers, or it could be 3 kilometers if it's seismic. And if it's in this east rift zone, it might be similarly 2-3 kilometers down like that as well. Right, Of course, from there, moving shallower into this shallower rock, that's what tells you if it's getting shallower from 3 kilometers towards the surface, then that tells you it's moving towards an eruption or an intrusion like that. That's the kind of thing we look for. So it really depends on where, and it's got to do with a pattern of earthquakes, but also the tremor, and that's why we've looked at that a little bit as well here and there, is the tremor being when magma is moving through the crack and just vibrating, right? Vibrating a wall just by flow, not unlike blowing through a small airway and making a whistling sound kind of thing.
All right. I believe this is the last question I have on deck for you. Let's see here. I just lost it. Oh, is there Stefan asks, is there a limit to the amount of swelling Kīlauea can take before it pops? Or is there some trigger level for the swelling?
It's a dynamically changing system all the time, right? And this goes back to the big picture of volcano swelling, but then it has a south flank. And the south flank is able to move out of the way, and just by it moving, it grows the magma reservoir. Because it displaces to the south, suddenly everything is less compressed, there's more space for it to spread. So the south flank moving makes a big difference. So if the south flank is stuck and can't move at all, then you might see, okay, now it's only magma, we can look at just magma. Is there a breaking point? Gets to that breaking point, now it's going to pop out, right? Whereas otherwise, it's getting to that breaking point. Is the south flank going to move instead of it popping out? Or is it going to hold still and allow it to pop out? And that's the dynamic we're always trying to figure out, and why all of our updates, we always mention the south flank, what the south flank is doing, and then what the summit's doing, and then rift zones as well. So that's the big picture of it. I didn't exactly, answer it. It varies, right? The giveaway is when we see everything quaking at elevated levels, then okay, that's about as much as you can take around there, and that's what we saw 2-3 months ago when we started saying, okay, this pattern means something's going to happen within months, and then it went from months to weeks, and then here we are.
Right. And we are now past the 3-month deadline, so there's no more question about if it erupts today, is it a new eruption? It is definitely a new eruption now. So that makes that a little bit easier. Now The question becomes, my question is how long is the clock on this intrusion relating to some future eruption? How long is that clock? Is it also 3 months to say that, this intrusion is related to it? If, say, the signal, it's close enough for the signal to be, debated if it's related to it, is what's kind of threshold in time. If it's 2 weeks from now, then we can obviously say, yeah, it's connected. If it's 2 months from now, it's a little bit of a harder sell off the.
Well, I mean, it's all connected in some way, anyways, right? We've gone back and we've looked at how eruptions that happen 5 or 6 years after some intrusion will move that magma and erupt it out of some random spot. So it can be years drawn out for years kind of thing, and certainly affects it. But to draw a straight connected dot line from 1 to 2 to 3 to 4, that's a lot harder to do for sure.
Right.
Yeah.
Especially when we deal in arbitrary time frames, like the 3-month threshold, right? It's really hard to confine everything into that little box or outside of that box. Right. We saw just last time how gray that gray zone that might just happen one day.
Right.
So yeah. All right, I think that does it for questions. I got no more here. We are going to be doing a premiere of another episode of Drones On, this time June 10th and 11th. Looking back at Fissure 8 and the 7-mile lava flow down to the Bay of Poho and the ocean entry there. Talk a little bit about the formation of beaches and some animal rescues, as well as the overflows of the lava channel a little more. So yeah, check that out. It's a short one. It'll be premiering immediately after this live stream. So with that, I think back to you, Phil.
Yeah, mahalo, Dane. So yeah, thanks for manning our streams and answering those questions online and collecting all that. Thank you guys for interacting with us, submitting your questions, and helping us all learn by just talking about it some more, right? That's our overall goal, is to talk about this every time so that we can raise our level of education on the island and off the island about how this volcano works, so that when it comes time to mobilize in response to something that threatens our communities, we can do so without worrying about the science of it and be a lot more of us knowing what goes on and how it works, and we can help calm the fears and put the concerns where they belong, where they can lead to action that's productive. Ultimately, that's our goal, right? Resilience of our communities in volcanic eruptions is why we do this. And so thank you guys for interacting and helping us do that.
We have a last minute $30 donation from our friend Gary Bryan. He says, thanks much. Appreciate it, Gary.
Mahalo, Gary. And my next thing was exactly that. Mahalo, all you guys, for supporting us and contributing with donations or just sharing, liking, and sharing a video. Thank you guys for doing that as well. That helps us build our base, and that it's all towards keeping this thing going, right? And it's always easier to keep it going at times like now when there's something exciting happening. But as you guys have seen, we've tried to keep it on the entire time, every week, when things are not happening as well, and that's where we really need your support. So if you're enjoying what we're doing here, especially when it comes time to mobilize when something exciting happens, and we definitely appreciate that. So mahalo once again. All right, so unless something else happens here, we will be back with you guys in another week and review what happens between now and then on Kīlauea, Maunaloa. We'll see if we can catch up to that volcano watch, whatever it is. Check hawaiitracker.com if you want to catch it before then. Otherwise, for hawaiitracker.com, we'll see you guys next week. He is Dane DuPont. I'm Philip Ong. Aloha, everyone.